Okay, today we'll be solving problem 5.13 from the heat and mass transfer 8th edition. Uh, Starting off with the problem statement in the textbook, it just gives a brief definition of what a kind of thermal energy storage system we are using. So it says thermal energy storage systems commonly evolve a packed bed of solid spheres through which a hot gas flows in the system and then charges, or a cold gas if it is being discharged. In the charging process, heat transfer from the hot gas increases thermal energy stored within these colder spheres. During discharge, the stored energy decreases as heat in is wait energy decreases as heat is transferred from the warmer spheres to the cooler gas. Sorry. And then it gives you a nice little schematic here of kind of how it's set up. Obviously, there would be more everywhere, but they give you that little bit of density there. And then it gives you the actual problem with the corresponding variables and what it wants. So we are considering a packed bed of 75 millimeter diameter aluminum spheres. It gives you all those properties. And it says, and we're in the charging process for which gas is entering the storage unit at a temperature of 300 degrees Celsius. It says the initial temperature is 25 degrees Celsius of the spheres and a convection coefficient of 75 watts per meter squared Kelvin. So firstly, it asks how long does it take the sphere near the inlet of the system to accumulate 90% of the maximum possible thermal energy? It asks what the corresponding temperature is at the center of the sphere, and then they want us to compare copper and aluminum, seeing if there's any advantage to using copper instead of the aluminum. So here's my given statement. Just discusses what we just read, and then find. So the time it takes for the sphere near the inlet to accumulate 90% of max thermal energy, its corresponding temperature at center, and then the advantage of using copper over aluminum. So here we see the schematic. I just drew the one ball, which we could see up here, or a sphere. So it's aluminum, and then I wrote down just the convection properties external of that. So then our assumptions, we know that it's a transient problem because they mentioned initial time or initial temperatures, and they're also asking for time. And then I just wrote down a simple one saying constant properties. I'm sure that you can find other assumptions, but for now, I'm just going to have these two. So first, we're going to start with finding the Biot number. Here we have the equation HLC over K. So in this case, we have LC, which is radius divided by 3, which is half of the 75 millimeter diameter that they gave us. Our H is 75 watts per meters Kelvin, and then a K value of 240 watts per meters Kelvin. So solving that, we get a value of 0.0039. And then to determine what kind of solution set we're going to use in transient systems, we need to compare our value to 0.1. So if our value is lower than 0.1, we use lumped, and then if it's greater, we use first term approximation. Here it is less than, so we are going to use lumped capacitance. So from here, we are going to start with the thermal time constant. We're going to solve for that. Here on the right, you could see the equation in the textbook. So here I wrote down T is equal to, or tau is equal to density times the volume times C over HAS. So just checking out what exactly goes into the volume and area calculations, we could then simplify that to just rho times the diameter times C over 6 times H. So plugging in the values that we have here, we find that our thermal time constant is 427.5 seconds. So from there, we can then use Q over Q max is equal to 1 minus e to the negative t, or time, over our thermal time constant. So we know that Q over Q max is the percentage we were given up here, so it's 0.9. And then just equivalent to what I said before, but now we're plugging in our thermal time constant of 427.5 seconds. So from here, we would just subtract, or we would add the E over here and then subtract the 0.9 from the 1. So we get 0.1 is equal to E to the negative T over 427.5 seconds. In order to remove E, or in order to remove E, we need to use ln, our natural log. So ln of 0.1 is equal to negative T over 427.5 seconds. Natural log of 0.1 is equal to negative 2.3, which is then multiplied by our 427.5, and it's equal to negative T. So those negatives cancel out, and you get a time of 984.4 seconds for it to accumulate 90% of the max thermal efficiency, or energy, sorry. So then for the next part, finding the corresponding temperature, we use our temperature ratio. So T minus T infinity, or T ambient, over Ti minus T infinity. And that's equal to E times our thermal constant times, or 1 over our thermal constant times T, as stated before. So from there, we can just simplify this equation, or we could just plug in 1 over 427.5 seconds in the E. And then we also know that our ambient temperature, or the gases, are 300 degrees Celsius. We don't know what that temperature is right now. We know that we initially started at 25 degrees Celsius for those spheres, and then once again, the ambient temperature. And that's all equal to E to the negative 1. This would be 1 over 427.5 seconds times T. So just rearranging that equation, we get our top portion here is equal to the difference here, which is negative 275 degrees C, times 0.0999895, which is just this term. So then we can multiply these and then add over that 300, which we get a temperature of 272.5 degrees Celsius. So the center of the sphere, after our 984.4 seconds of heating, turns into 272.5 degrees Celsius from that 25 originally. Now we are checking the average of or the advantage of using copper. So copper's characteristics are given here: density of 8,900 kilograms per meters cubed, and in our C value of 380. So we're just going to follow the same steps real quick here. We know that Biot number is not going to change. We still have the similar values. Actually, you should check the K value. Since we have a new element, or a new metal being used, you should really check that. I happen to forget it, but just due to the pathing of the equation, I know, or the question, it's all on lumped capacitance, so I know that's going to be lumped. So just following the steps from before, we now get a thermal time constant of 567, or 3.67 seconds. So a little bit longer than the 427 than we had originally with aluminum. I just simplified these equations because I know most of this isn't going to change except for the time constant. So I got a total time of 1,296.43 seconds in order to reach 90%. And that, compared to the original one, is around 300 seconds longer. So the copper is going to take a little bit longer to heat up. So I guess if you wanted something that would take longer to heat up, you would use the copper. But most of the time, what you're going to want to use is that aluminum, because it's going to absorb more heat faster, reducing or increasing the efficiency of the system. And then I just solved for the temperature, which is basically the same thing as we got up here, 272.5 degrees Celsius. So like I said here, it takes longer to accumulate the energy. So it's not really an advantage, or there's not really an advantage to using the copper. It's better to just stick to the aluminum and absorb the heat faster for a more efficient system. So yeah, that's the question. Thank you. Sorry, it was a little rushed, but yeah, good day.